Good day everyone. So from this video, we will discuss some topic about highway and railroad engineering. The first topic is the scheme appraisal for highway projects. The aim of the highway appraisal process is therefore to determine the economic, societal, and environmental feasibility of the projects or group of projects under examination. The process enables highway planners to decide whether a project is desirable in absolute terms and also provides a means of choosing between different competing project options, all of which have the ability to meet the stated goals and objectives of the project is concerned. Under that scheme, meron tayong tatlong method. Dito pumapasok yung economic appraisal of highway scheme. Some of the goods provided by the public sector such as defense, schools, and roads are not directly charged for. Consequently, financial criteria are of little help in ensuring that money is spent in a consistent and efficient manner and that benefits to society from investment and maximize. Cost-benefit analysis is a technique which has been developed to assist in the appraisal of a non-marketable output of public sector investments. Cost-benefit analysis. Cost-benefit analysis or CBA, a Department of Transport-sponsored computer program, estimates the effect of highway improvements in terms of time, vehicle operating, and accidents costs on the users of the road system. These cost changes are compared with the construction and maintenance costs over the appraisal period. Traffic flows with, with and without the scheme being appraised are input together with a detailed geometric description of the network links and junction. The individual link and junction user costs are summed to yield the total cost over the network. So, ang cost-benefit analysis ay may mga step. Una nandito ay ang identification of the main project options. Ito ay first step na kung saan magamit to identify the alternative option to be considered. The option under consideration were specific to the particular problem and context, but under other circumstances may have included investments, projects, policies, and development plans. It was important to have a clear and detailed description of what each option was was as detailed in the following section. Next ay ang identification of all relevant costs and benefits. When then identified all negative impacts, which is the cost, and positive impact, which is the benefits related to each option under consideration. If known, it is useful to describe the geographical and temporal boundaries of the analysis. Example is the area and number of years over which costs and benefits are expected to occur. Next step ay ang economic life residual value and the discount rate. Highway project is often complex and long-term, with the costs and benefits associated with it occurring over a long time frame, which determine the life of the project. A parameter dealt with in earlier chapters. It sets a limit on the period over which the costs and benefits are estimated, as all must occur within this time slot, be it 25, 35, or even 50 years or more. It is related in principle to the expected lifetime of the project under analysis. In addition to this, the costs and benefits occur at different times over time horizon. Because of this, they cannot be directly combined until they are reduced to a common time frame. This is achieved using another parameter introduced earlier, the discount rate, which translates all costs and benefits to time equivalent values. The actual value used is the social discount rate, given that the decision maker is interested in the benefits and costs to society as a whole rather than to any individual or group of individuals. So the next topic is the use of economic indicators to assess basic economic viability. Once the two parameters of project's life and discount rate are set in place, this allow all costs and benefits to be directly compared at the same point in time. The decision maker must now choose the actual mechanism for comparing and analyzing the costs and benefits in order to arrive at a final answer for the net benefit of each of the project options under consideration. Any of three techniques listed earlier in the chapter can be used for this purpose. So, yung tatlong method na yun ay ang net present value or NPV. Another one is internal rate of return, which is IRR, and last is benefit or cost ratio or B over C. All these are based on discounted cash flow technique of discounting all future costs and benefits to a common year. Ano nga ba yung sinasabing net present value method? In this method, the stream of cost benefit associated with the project over an extended period of time is calculated and is discounted at a selected discount rate to given the present value. Benefits are considered positive and cost is negative, and their summation gives the net present value. Any projects with positive NPV is treated as acceptable. In comparing more than one project, a project with a higher NPV should be accepted. So the next is benefit cost ratio method. These are the number of variations on this method, but a simple procedure is to discount all costs and benefits to their present worth and calculate the ratio of the benefits to cost. Benefits are positive flows while costs are negative flows. Thus, the savings in transport costs are considered as benefits. If the benefit cost ratio is more than 1, the project is worth undertaking. The last method is the internal rate of return. The internal rate of return is the discount rate which makes the discounted future benefits equal to the initial outlay. In other words, it is discount rate which makes the stream of cash flow zero. Next step is the advantages and disadvantages of cost-benefit analysis. Advantages: the use of common unit of measurement, money, facilitates comparisons between alternative highway proposals and hence aids the decision-making process. Next is a cost-benefit analysis is in part a tool geared toward helping you to make rational rather than emotional decisions. Disadvantages: the method is more suitable for comparing highway proposal design to meet a given transport objective, rather than evaluating the absolute desirability of one project in isolation. Next is the primary basis for constructing a highway project may be a societal or environmental rather than an economic one. Last step is the payback analysis. Payback analysis is a mathematical methodology to determine the payback period for an investment. The payback period is how long it will take to pay off the investment which with the cash flow derived from the asset or project. In colloquial terms, to calculate the break-even point, the payback period is usually measured in fractions of years. Payback analysis can provide important information for decision making. It provides a, it provides a means to manage risk. You can use payback analysis to determine whether an asset or project will pay for itself in a acceptable period of time. Shorter payback periods are usually viewed as less risky. Additionally, you can also use the method to compare potential assets or projects to see which will regroup its costs quicker. The payback method is certainly not the only financial metric that should be relied upon when making an investment decision, but it is a useful tool. The following formula enables the payback period to be to be arrived. Payback period is equal to CO plus NAS, where CO is the initial construction cost of the highway project, while NAS is the net annual savings. So, ang next naman natin ay ang environmental appraisal of highway scheme. Roads attaches great importance to environmental issues. Environmental assessment is a method and process by which information about environmental effects is collected, assessed, and used to inform decision making. The main aims of an environmental assessment of road schemes are to ensure that the likely environmental effects of possible scheme are fully considered so that decision can be made with a knowledge of their environmental consequences, including the decision whether or not to proceed with the further development of the scheme, and if it were to go ahead, to aid the identification of ways in which the environmental effects could be minimized through route selection and other measurement or other measure. Next is to ensure consideration of the likely environmental effects of route options in a way which enables the importance of the predicted effects and the scope for mitigating this to be properly evaluated. Last one is to allow the public and statutory environmental bodies to comment on the proposal taking account of their environmental implications. Within the UK, since 1993, the Design Manual for Roads and Bridges has provided the format within which the environmental assessment of highway schemes has taken place. It identified 12 environmental impacts to be assessed for any new improved trunk road proposal. The 12 environmental impacts forming the assessment frameworks are: first is the air quality, cultural heritage, construction disturbance, ecology or nature conservation, landscape effects, land use, traffic noise and vibration, pedestrian, cyclist and community effects, vehicle travelers, water quality and drainage, geology and soils, and lastly is the policies and plans. Last method ay ang the new approach to appraisal na tinatawag na NATA. The new approach to appraisal was the name given to a multi-criteria decision framework used to appraise transport projects and proposals in the United Kingdom. NATA was built on the well-established cost-benefit analysis and environmental impact assessment technique such as those contained in the Highway Agency Design Manual for Roads and Bridges for assessing transport projects and proposals. In April 2011, the coalition government decided that the term NATA would no longer be used. However, the principles and key elements of the NATA framework remain in the Department for transportation (TAG Transportation Analysis Guidance). The method for assessing the value of money of transport projects have been at the forefront of the project appraisal practice in the UK for many years. NATA was designed to build on that good practice by bringing together the mass of detailed appraisal information about the impacts of a transport proposal, some of which are expressed in monetary terms, some using quantitative measures, or just in qualitative terms. A key aspect of NATA is the use of standard worksheets to calculate the large amount of cost-benefit analysis and environmental impact assessment data and then present it in a more concise, consistent, and balanced way. Within the NATA framework, the impacts of transport projects are categorized in terms of five high-level criteria. Ito ay ang economy, safety, environment, accessibility, and integration, reflecting the government's objectives for transport. Each of these criteria are divided into a number of sub-criteria, and it is against each of these sub-criteria that the impact of a proposal are assessed and presented in a page 1 appraisal summary table. The division of the five criteria is shown below. First is the economy. Under ng economy, nandito ang public accounts, transport economic efficiency, business users, and transport providers. Transport economy efficiency, consumer, reliability, wider economic impacts. Next is the safety. Under nito ang accidents and security. Next is the environment. Under nito ang noise, local air quality, greenhouse gases, townscape, heritage of historic resources, biodiversity, water environment, physical fitness, journey, ambience. Next is the accessibility. Under nito ang option values, severance, access to the transport system. And lastly is the integration. Under nito ang transport interchange, land use policy, and other government policies. So, the next topic will be discussed by Dexelle Palomares.
Good day everyone. Here is the continuation of our topic, which is the basic elements of highway traffic analysis. The functional effectiveness of a highway is measured in terms of its ability to assist and accommodate the flow of vehicles with both safety and efficiency. In order to measure its level of effectiveness, certain parameters associated with the way must be measured and analyzed, and these are the properties include the quantity of traffic, the types of vehicles within the traffic stream, the distribution of flow over a period of time, which is usually 24 hours, the average speed of the traffic stream, and the density of the traffic flow. Analysis of these parameters will directly influence the scale and layout of the proposed highway, together with the type and quantity of materials used in its construction. This process of examination is termed traffic analysis, and the sections below deal with the relationship between the parameter which lies as its basis. Speed, flow, and density of a stream of traffic. The traffic flow Q, a measure of the volume of traffic on a highway, is defined as the number of vehicles N passing some given point on the highway in a given time interval T, with the formula Q equals to N over T vehicles per unit time. The number of vehicles on a given section of highway can also be computed in terms of density or concentration of the traffic. K equals to N over L, where K is the measure of the number of vehicles N occupying the length of roadway L. For a given section of road containing K vehicles per unit length, the average speed of the K vehicles is termed the space mean speed U. The average speed for all vehicles is given at a given discrete point in time. The fundamental traffic flow. Characteristics are flow, speed, and density. We define flow as the number of vehicles passing a point in a given time period. Speed is a vehicle's rate of motion. We define traffic density as the number of vehicles occupying a unit length of roadway at an instant in time. Traffic flow demand represents the demand on a transportation system. The comparison between this and the capacity determines a facility's operational performance. Traffic flow measurement has many uses in the planning, design, and operation of highway facilities. Planners use flow measures to classify streets, identify traffic trends, study origin-destination patterns, and predict revenue. What is flow? We define flow rate as the number of vehicles passing a point in a given time period, usually expressed as an hourly flow rate. Flow or flow rate has gradually replaced the term volume over the years. Because flow rate varies over time, not only do we need to define but also the time period over which it was measured. Speed. The second fundamental traffic flow characteristic is speed. There are two ways to measure speed. Time mean speed, which is known as TMS, and space mean speed, SMS. TMS is calculated from the individual speed recorded for vehicles passing a point over a selected time period. SMS is calculated by dividing the average travel time by the measured distance. Speed and travel time are fundamental measurements of a highway traffic performance, and speed is a key variable in the design of roadway facilities. Density. Traffic density is the third fundamental traffic flow characteristic. It is an important characteristic that engineers can use in assessing traffic performance from one point of view of users and system operators. Engineers also employ it as the central variable in freeway control and surveillance system. Speed density relationship. Speed density relationship is straightforward and easy to explain when compared to other fundamental relationships. It is a one-to-one relationship between the driver behavior and the number of vehicles present on the road. Speed density relationship is also a part of traffic dynamics studies to explore traffic flow patterns such as shock waves and queue lengths on highway and urban arterials. This is the graph showing the relationship of speed and density. Flow density relationship. The flow and density varies with time and location. The relation between the density and the corresponding flow on a given stretch of road is referred to as one of the fundamental diagram of traffic flow. Some characteristics of an ideal flow density relationship is listed. When the density is zero, flow will also be zero since there is no vehicle on the road. Second is when the number of vehicles gradually increases, the density as well as flow increases. When more and more vehicles are added, it reaches a situation where vehicles can't move. This is referred to as the jam density or the maximum density. At jam density, flow will be zero because the vehicles are not moving. There will be some density between zero and density and jam density. When the flow is maximum, the relationship is normally represented by a parabolic curve. This is the parabolic curve of flow and density. Speed-flow relationship. The speed-flow relationship is important to traffic engineers as it forms the basis for trafficking planning and design. The relationship between the speed and flow can be postulated as follows. The flow is zero either because there is no vehicles or there are too many vehicles so that they cannot move. At maximum flow, the speed will be in between zero and free flow speed. The graph showing speed and flow relationship. Next is determining the capacity of highway in the level of service approach. One of the most critical needs in traffic engineering is a clear understanding of how much traffic a given facility can accommodate and under what operating conditions. These important issues are addressed in highway capacity and level of service analysis. The basis for all capacity and level of service analysis is a set of analytic procedures that relate demand or existing flow levels, geometric characteristics, and controls to measure of the resulting quality of operations. Highway capacity. The capacity of a facility defined as the maximum hourly flow rate at which the maximum number of vehicles, passengers, or the like per unit time, which can be accommodated under prevailing roadway, traffic, and control conditions with a reasonable expectation of occurrence. Capacity is independent of the demand. It speaks about the physical amount of vehicles and passengers that a road can afford. It does not depend on the total number of vehicles demanding service. Generally, the highway capacity depends on certain conditions as listed. First is the roadway characteristics. These are associated with the geometric characteristics and design elements of the facility, which include type of facility, number of lanes, lane width, shoulder width, horizontal and vertical alignments, lateral clearance, design speed, and the ability of queuing space at intersections. For example, is a curved road has lesser capacity compared to a straight road. Second is the traffic conditions. Capacity expressed in terms of units of some specific thing, so it also depends on the traffic conditions. The traffic conditions are associated with the characteristics of the traffic stream on the segment of the highway. This include the distribution of the different type of vehicles in the traffic stream or traffic composition, such as the mix of cars, trucks, buses, etc., and the directional and lane distribution of the traffic volume of the highway segment. Furthermore, it includes peaking characteristics, portions of turning movements at intersection. Third, control conditions. This primarily applies to surface facilities and includes the types of traffic control devices in operation, signal pacing, allocation of green time, cycle length, and the relationship with adjacent control measures. Level of service. The level of service concept was introduced in the 1965 HCM as a convenient way to describe the general quality of operations on a facility with defined traffic roadway and control conditions. Using a letter scale from A to F, a terminology for operational quality was created that has become an important tool in communicating complex issues to decision makers and the general public. The intention of LOS is to relate the traffic service quality to a given flow rate of traffic. It is a term that designates a range of operating conditions on a particular type of facility. Highway Capacity Manual, or the HCM, provides some procedure to determine level of service. It divides the quality of traffic into 6 levels ranging from level A to level F. Level A represents the best quality of traffic where the driver has the freedom to drive with free flow speed, and level F represents the worst quality of traffic. What are the factors affecting level of service? One can derive from a road under different operating characteristics and traffic volumes. The factors affecting level of service can be listed as follows. First, speed and travel time. Next is traffic interruptions restrictions, freedom to travel with desired speed, driver comfort and convenience, and the operating cost. In terms of two-lane highways, capacity of a two-lane highway is 1,700 passenger cars per hour for each direction of travel and is nearly independent of the directional distribution of traffic. For extended segments, the capacity of a two-lane highway will not exceed a combined total of 3,200 passenger cars per hour. Short sections of two-lane highways such as tunnel or bridge may reach a capacity of 3,200 to 3,400 passenger cars per hour. And in multi-lane highways, it also shows that the capacity of a multi-lane highway under base condition is 2,200 PC over H over LN for highways which with a 90 km per hour free flow speed. At flow rates between 1,400 and 2,200, the speed on a multi-lane highway drops, for example, by 8 km per hour for highways with a free-flow speed of 90 km per hour. Sizing a road using the HCM approach. As highways become more and more congested, the understanding of traffic operations evolve along the needs of the practicing transportation professional. Evaluating congested operations, considering multiple modes and their interactions, and obtaining a variety of performance measures and tools, including simulation, become increasingly important. HCM resources can be applied to estimate of queue length, travel time, reliability, and other operational design and planning analysis. HCM still provides methods for the more traditional analysis of uninterrupted facilities such as freeways, multi-lane ways, and two-lane ways, and for interrupted facilities such as urban streets, interchanges, signalized intersections, unsignalized intersections, and roundabouts. Estimation of AATD, or the annual average daily traffic values. For road transport planning and air pollution, mapping and modeling street level, annual average daily traffic values are an essential input. Major roads in many developed countries are now equipped with automated traffic counters, tolling system, and other technologies that can deliver regular and reliable data on daily traffic flows. And that's the end of our topic. That's all. Thank you.